conscious part was holding off momentarily irrelevances to the situation, the constellation that I was concerned with. And having discovered that my conscious part was this holding off irrelevances, I found that the irrelevances fell into two main categories. All the irrelevances were all the experiences which were too large and too infrequent in any way alter or tune in with the magnitude of relationships I was considering, and all the experiences in my life which were too high frequency, too small to in any way be measurable at the magnitude I'm considering. So that was really a tunable set. And because the experiences were inherently omnidirectional observations, because our Earth is revolving and we are revolving and we're going around the sun, continual readdressing of our view in many, many directions, then the dismissal of the irrelevance into a macro and a micro group was an omnigeometrical phenomena, sending them outwardly and inwardly, and there was then a lucid set of stars that were quite clearly relevant to one another, and that lucid set then defined an insideness and an outsideness. They were between the outsideness, the macrocosm, insideness, and the microcosm. And we then found that the minimum number of stars that could define an insideness and outsideness would be a tetrahedron. That is, the 2 points had between us but no insideness, outsideness. 3 points had between us but no insideness, outsideness. Not rather 4 points. So as we came to a system, and we're looking for the fundamental number of interrelationships of some things that provoked us. We didn't know what other items might be in it. If we only saw 3 of them, there could very readily be a 4th one. So as we began to really dismiss properly, we'd find out which side that 4th one might be to give the insideness and outsideness. And we found that there were 4 points, but also the 4 points have 6 interrelatednesses. So we have a prime number 3 and a prime number 2 geometry being generated here by the process of thought. And then I developed a great deal more with you on the idea of the tetrahedron then being the minimum system, because I defined a system as an aggregate of events that divided the universe into all the universe outside the system, all the universe inside the system, a little bit of the universe which is a system, which is the defining subdivision. The tetrahedron is a minimum system of universe, and it turned out to be then omnitriangulated. We found that structures are always triangulated. Structure meant triangle, triangle meant structure. There were no other stable polygon. Therefore, tetrahedron turned out to be the minimum structural system of universe. We did a whole lot more exploring, reviewing about tetrahedra, the cheese platonic solids, and the splicing parallel to the faces of them, and discovering that all of them were made asymmetrical by such slicing, with the exception of the tetrahedron. Simply became a smaller but absolutely regular symmetrical tetrahedron if we sliced parallel to any of its 4 faces. So we found it's the only geometry that could accommodate, whose symmetry could persist as a symmetrical system universe, and yet accommodate alterations, aberrational alterations, uneven alterations. The other geometries could not coordinate such phenomena. So we found that everything was reference to 4 planes that were subtending the 4 vertexes of the tetrahedron, so that we were dealing in a basic 4-dimensional system. I've made many references since that time coming back to tetrahedron and structures, and we get into then just recognizing late yesterday that in the water people and the mathematics of the water people coming from the Indian Ocean to Babylon to Crete and then to the Ionian Greeks, the possibility that the king's symbol of the hexagon, the 6 equilateral triangles, and the household or the distaff side using the square somehow indicated that they got into the public domain, general domain, for the first time in history, the mathematics in terms of reference to XYZ coordinates of the square, but not in relation to the XYZ, the WXYZ of the four axi of symmetry of the four triangles of the tetrahedron. So that we find dimensionality suddenly then being identified with the previously by society only with perpendiculars to the system, assuming you have to have rectilinearity. But we find then if you can have four sets of perpendiculars to the tetrahedron to symmetry, and this is the only sort of fundamental symmetry that's not altered, so that we find that this four-dimensional quality of the tetrahedron makes it possible to model four-dimensional, five-dimensional models, whereas you could not model with cubes anything more than 3 dimensions. Fourth dimension was not accommodated. So that we found that the tetrahedron volume was 1 and the cube is 3 when the volume is 1, so that if you use cubes, you're using up 3 times as much space to identify the number agglomeration, and the tetrahedron then seemed to be not only nature's basic, simplest structural system in the absolute limit case, but it also then seemed to be the basic unit of quantation, and we found that we were able to identify that with the quantum mechanics with 1 unit of quantum. So I'm now going to develop some more with you today of the synergetic geometry. And our book will be coming out, I was told today, approximately, be published, I think, the 3rd of April. And the editor of Macmillan's is here with us tonight out in the control room, and it'd be a good idea for him to experience with us a little of the synergetic geometry. I'm going to review quite quickly the hierarchy of values of the synergetic solids, in contradistinction to the lack of being able to have a hierarchy of values when you use the cube as unity and use the edge of the cube as your unit of linear measure. Then you find that the tetrahedron of equal length edge, or the octahedron, or the icosahedron, all the other Platonic solids, their volumes are irrational numbers in respect to the cube. Whereas with the tetrahedron as unity, and the edge vector of the tetrahedron being the diagonal of the cube rather than the edge of it, because it is necessary. The cube does not, as we saw, have any structural stability without the triangulation, and only when you put in the diagonal into the cube do you have stabilization of it as a structure. So that we see then we have to have it's the diagonal of the cube that makes it a structure. So if I consider only hierarchy of structural solids, where the integrity of the form of the solid is actually guaranteed by being properly triangulated, then we find that the volume of the cube is 3, the volume of the octahedron we showed you was 4, the volume of what we call the rhombic dodecahedron, this form here, is exactly 6, and go on to what we call the vector equilibrium. I gave you the pumping one that fills all the space, which was the form of 12 spheres close packed around one sphere. It is the first nuclear array. There is no inherent sphere at the center of a cube, and you cannot get a stable cube made out of spheres until we get to a very high frequency number of those cubes of the spheres. But we have the first fundamental nuclear system is then the growth of layers of spheres around a nuclear sphere. That gives you then the 12 around one, and the 12 around one gives us then the 12 vertices of the vector equilibrium. This is just to remind us of the fact that the cube does not have any stability by itself. The rubber joints give it a little bit, but that's where you put triangle. There's a little triangulation, like triangular gussets in the corners, provided by the webs of the rubber. So it's triangulation made the same. Here's our vector equilibrium, and here are then the 4 vertexes in the northern hemisphere, 4 down there, and we got then the 6 around the equator. There's our 12. Now, the volume of the vector equilibrium is 20 when the tetrahedron is 1, and it consists then of, you can see the 8 tetrahedron. The tetrahedron goes from this triangular face into its center. There are 8 such triangular faces, so you get 8 tetrahedra in here. That comes from each of these square faces is the cross-section of an octahedron. It's a half octahedron whose vertex is the center. And the octahedron had a volume of 4, so a half octahedron is a volume of 2. And I have 6 of those square faces, so 6 times 2 is 12, plus the 8 tetrahedra, which are a volume of 1 each, and makes a total of 20. This vector equilibrium is 20. And we saw that this really then is the maximum domain of a nucleus. One of the things I started to really search for in the early days of the energetic geometry, it was the following. I said it could be that we might find some patterns in the universe in relation to something where there was really specifically a nucleus. I found there was no inherent nucleus in the cube. If you just try to take one sphere and put 8 spheres around it for corners, they just fall off. There's absolutely no structural stability whatsoever. So I want to have a nuclear array, and this is the minimum nuclear array. And that began to really intrigue me, and so I said it could be that around a nucleus there are a set of pattern evolvements. As I have progressive layers, for instance, I put on more spheres, where there may be a unique set of pattern experiences, but you may come to a point where they suddenly repeats the early one. There may be a limit set of absolutely unique nuclear pattern interrelationships. And I found that's exactly what happened. I'm going to need to use my board tonight. And we'll have a red nucleus here. And now I'm going to draw myself a hexagon to make this a little easier to do. I could have another then sphere here. Overdone them a little, sorry. Anyway, I have then a hexagon suddenly showing up in here. This is in a plane 6 around 1. Then I find that you'll see that between these 3 balls here, there's a nest here. Therefore, I can nest a ball on top of that. When I do that, then I overlap this one too much, so I can't get one on here. I can have one, however, in this nesting. This is pretty bad drawing, I'm sorry. But there's a nest in here. So I can have one here, and one here, and one here. 3 balls can nest on top of here and touch each other. You may remember when I have 3 balls on the... 2 can touch each other, 3 can touch each other, no question about it. That gives you a triangle. Then there's a nest on top. We're going to have a 3rd ball sit on top, the 4th ball. That made tetrahedron. So I'm really reversing now. There's one at the center, and then 3 are on top of it. I'm sitting in those nests. I get 3 on the other side, and they give me then the 12 spheres around 1. But I want you to think about it for the moment just in a plane, and quite clearly this is rather a stable affair. Doesn't seem to be trying to do anything to us. I could have another layer of balls, though. I'm sorry I'm making such a mess of my drawing. Seems to have been trouble up in this space here. Now, you say, I don't think anything is happening. You just put another row around, that's all. But you find that I put 6 around here the first time. In the second row, if you count them up, you find that there are 12. There's 1, 2, 3, 4, 5, 6, 7, 8, 10, 11, 12. And so you've added, each time, first I had 6 sets of 1, now I've added 6 sets of 2. So I have really then a basic 6ness around it because it's a hexagon. But I find that there, because there were 6 in the first row and there are 12 in the next row, that makes 18 of them around 1. So in 6 sets, then there must be 6 sets of 3, because 6 times 3 is 18. So I want to collect these in 3s. So I can do this. Those 3. And then I take these 3 here. Yeah. That's where that. Then I take this 3 here. This 3 here. This 3 here. And this 3 here. You'll find that those are turbining around. You see the turbine action? The minute I put an additional layer then, the first layer didn't try to do anything. With one more layer on this trying to go around. I could have taken, instead of these 3, I could take these 3. If you do, then it wants to go the other way. But the minute there's a third layer, they have to go somewhere. It sets up a dynamic patterning. There's quite a little difference in the situation if I have a light. These are transparent spheres. I have a light at the center here, and its relationship to the nucleus, it gets a very beautiful direct lighting, just tangent. But this next ball here does not have the same amount of light coming to it. So that is a unique pattern. I want to introduce different things that are going on here as the second layer comes in. If I put on a third layer, I've got a second, now I get into a third, you'll find the same thing happens. From here on, it's always turbining. Only a first layer does not turbine or want to go anywhere. It's really a neutral. I then found, if I began to have the balls around, coming around, growing around it in all directions, if I had the 12 on here, then this next layer I get a filling in. Every time it comes out the same shape, the vector equilibrium. Always has the 8 triangles and the 6 squares. Every time I keep enclosing it, it comes out that way. I don't think we have any models of that here in the room. Now, I found then that the first, we have a ball at the center. It is 0. There's no layers. It's 0. If I call these layers, there's a 0 layer. And then we come to the next one. We have 12 balls, the first layer. Next layer, we get there are 42 balls. And the third layer, there are 92 balls. If I have a fourth layer, that turns out to be 162 balls. My fifth layer is 252 balls. I found no matter how many layers I had, it always ends in the number 2. When I then recognize that this is a decimal system that I'm counting in, the congruence of modulo 10 is called, I have a constant suffix of the 10, so I take the 2 away. That leaves me, instead of the, it gives me a 10, 40. If I just take out 2 and say plus 2 to all of them, then this would be 90, and 160, and 250. Now each one of those is divisible by 10, so I do that. I get the numbers 1, 4, 9, 16, 25. And you suddenly recognize that as first 1 to the second power, 2 to the second power, 3 to the second power, 4 to the second power. So this, what's going on here is that I call this frequency of modular subdivision, F is my frequency, beautifully done. And we find that the frequency, I gave you also something, the physicists have two kinds of acceleration when I talked about precession, remember? There's angular acceleration when you're holding on to the ball, it's going around in a circle, and linear when it goes away. The radials are going away, they are the linears, and this is the angular going around like that. Now, whereas in a square system, or an XYZ system, in order to identify any point in geometry, they always have to go follow the lines. You can't take a diagonal. You can't take a diagonal like that. As that you can't, there's no short way. You can't go from point A here to B on the diagonal. You have to go through C. In fundamental analysis, algebraic analysis of any positioning of any points. But in the 60-degree coordination, because you see then the hypotenuse and the legs are never the same, so the angular acceleration will not be the same language as the radial, or linear. But and here the linear and the angular are the same. Exactly the same size vector, same energy effect. Remember what a vector means. Vector means, vector is represents an energy event, and it represents a mass times a velocity in a given direction in respect to observer. There's an axis of observation, we have a special angle, observer is moving. And the mass then times velocity gives you a discrete length of line. Vectors are not lines that go to infinity. They're inherently limited. So that when I talk about a vector, these vectors in a vector equilibrium, these represent forces of the universe in balance. The tendency to explode, I showed you the other day, being exactly countered by the contractive forces. So that the hexagon had 6 radials trying to explode and 6 chords. But the 6 chords are more favorably arranged because it is a chain. There is mass interattraction, so they get in critical proximity end to end, and they hold together, whereas the 6 other try exploding, they're disintegrating, not helping one another. The other 6 help one another. So that we have then, in the synergetics of counting, a space between 2 balls in closest packing is then a wavelength, and you don't have a frequency until you have at least 2 wavelengths. So frequency doesn't really begin until you get to this layer out here. In other words, frequency doesn't occur until that turbine, or the disturbing quality enters. It is trying to do something. It tries to go somewhere. And so this is frequency. This is, when you get out here, is frequency 2. Second power. So I'm going to then find a point that we have down here. The numbers of balls in any layer in the closest packing of spheres will always be frequency to the second power times 10 plus the number 2. That became a really fascinating kind of a matter. There was every layer had 2 balls assigned to the function of being a neutral axis. There were 2 extra balls for every layer to take care of neutral axis of spin. The nature provided that. And then if you ever thought about Victrola record, this part's going this way and that's going that way, the 2 opposite sides, get the center where nothing's going anywhere. There is literally a neutral axis theoretically there, but you've never been able to demonstrate it in 3 dimensions. But in 4 dimensions you can. I'm going to show it you right immediately now. Come back to our model of the vector equilibrium here. And I will have then, I can get, there are 2 balls, let's say, in every layer that can account for it being a neutral axis. And I'm going to take a vector equilibrium like this, and I'm going to, I said, lower the top triangle towards the triangle on the floor. I'm not allowed to twist. This is the axis here. I'm not allowed to twist the axis. It simply contracts in length. It does not twist. I do so, but the equator goes around. Here you see then the axis absolutely neutralized, and just able to introduce the motions, the equatorial motions. So we were able to also make this model, as you see later on, where we make these with wheels that are going, so it doesn't have to stop. They can keep on and on and on accommodating, but the center axis is absolutely immobile. When you get in these four-dimensional systems, one system like this then can latch onto another on the neutral axis without in any way frustrating the motions which they are participating. It becomes an extraordinary kind of accommodation that we experience in our actual life. We've never been able to accommodate in any three-dimensional model, but a four-dimensional model is right there. So we find that two-ness is a fascinating matter. Euler, I told you, developing his incredible realization that all visual experiences were reducible to three main aspects: the lines, the crossings of the lines, and the areas bound by the lines. Never to be ever confused one with the other, and that in a picture on a polyhedron and face, or a polyhedron itself, the numbers of vertexes plus the numbers of the areas will equal the numbers of the lines plus the number 2. Absolutely infallibly. But if you make a donut, I said, put a chord through it, really where we got that axis there, then the numbers, he said, of the vertexes plus the numbers of areas equal the numbers of the lines. The 2 have disappeared. I don't know why Euler did not identify that with the axis, because Euler has also made one very great, what we call structural engineering analysis. Structural analysis goes back to Euler. He's the first to develop then the concept of a neutral axis of spin of all systems. So it's a structural memory, very odd-shaped. If you have to find out what its neutral is for its dynamic, and he knows exactly how he's going to get your bendings and so forth. We find then why he didn't think of the two-ness of his own formula as representing the poles of the neutral axis, I don't know, but he didn't. But I found he had, and therefore it became very exciting to me. I said, I'm going to now always assign 2 of every layer of my balls, because he didn't get into this ball kind of pack. He didn't get into these layers of closest packed spheres. And closest packed sphere, this way all the atoms are all packed, so it's a very extraordinarily important kind of a pattern to be considering. And as we're dealing with atoms and we're dealing with the nucleus, and it has an inherent nucleus. No other geometry I know starts with an inherent nucleus. It's the only one. Closest packed and has nucleus. And this in every way conforms to all of our experience with the atom. So that I found then by taking 2 of every layer, they will always then take care of the neutral axis of the system. Therefore, I'd be able to latch onto any other system, and we can keep on accommodating all the kinds of things we do. Now, this was a very exciting discovery. I've spoken about an inherent nucleus. It is possible to get a nucleated cube, but it has to have many, many layers before a sphere tends to come in the center of the aggregation in pure symmetry. You can get a nucleated tetrahedron, and you can get a nucleated octahedron, and they occur very much more early and very much less aggregation than does the cube. There's a hierarchy of behavior going on here now. In this particular formula, we're then dealing with the vector equilibrium has a volume of 20. You remember? And also, I showed you that going from this closest packed condition, where there is a nucleus, I took this thing and I made it contract symmetrically. You remember? All the 12 vertexes work towards common center at the same rate. Remember, it finally gets to be octahedron. They're all doubled up. As all the vectors came towards common center at a constant rate. And as I drop this then, lower this towards the other side, notice these 6 squares begin to change. Triangles can't change. They are structural. Squares are unstable. They do change. We're now at a point where this thing is contracted slightly, but it's at a point where the short diagonal of those diamonds is exactly the same length as this chord. Therefore, you put this in, there are 6 squares, became 6 diamonds, you put in the 6 cross members, and you have your icosahedron. So the icosahedron is a contracted form of the vector equilibrium. It still has the same 12 vertices, same balls, but because it's contracted, there isn't room for the nucleus anymore. It becomes exactly the same phenomenon. One thing, it does not have a nucleus. Or you have compressed the nucleus, but you say you really can't compress that nucleus, so I have to really consider it does not have it. So I find then vector equilibrium is in a sense a vitiated or an empty, unoperated one. I have an operative one which has a nucleus. This you get in very much the relationships then between our proton and our neutron. So I find then the icosahedron has a volume of 18.51, where vector equilibrium is 20. It's a very interesting number because if you take the relative mass, relative weight of the electron in respect to the proton, and it is 1/1851. It's a really kind of familiar kind of a number in here. So this has something, when we get into the icosahedron level, with nothing at its center, it has something to do with electrons. But you could not take the icosahedron and pack them with other icosahedron and fill all space. They will join to one another and will finally produce a geometry to come back to the octahedron. But they make a very wide open octahedron. But they will not make themselves. And we find then they cannot be multi-layered, because as not only can they not have a ball at the center, but as you go from the outer layer into this, the collapse, and there's not room for another layer, so they can only be single layer. Icosahedron is always single layer, but it has other qualities that are very close to the same as vector equilibrium, and so vector equilibrium has a characteristic of 20ness, and the prime number 5 is in it. Whereas in the octahedron they have the prime number 6, there are 6 vertexes, and there are 4 faces and so forth. Prime number 2 is in there, prime number 3 is in there. But in vector equilibrium you first come to the number 5, prime number 5 is in there. And we find the icosahedron the same prime number 5, it's the pentagon 5 around each corner and so forth, and it is very fundamentally 5ness. That 5ness is in here as a basic characteristic of either the vector equilibrium, and by the way, vector equilibrium I now write this way because I have to keep saying it all the time, so I use that symbol for it. And so this here is really 2 times 5 times frequency of the second power plus 2. There's a multiplicative 2 showing here, and there's an additive 2, with the prime number 5 and frequency of the second power. As frequency of the second power is a very intriguing matter, because we have now layers, something growing around absolutely symmetrically like waves. It's an omnidirectional wave phenomenon, and every wave characterized by, say, the electromagnetic fundamental wave phenomenon, omnidirectional waving, propagation. And in respect to it, we have, remember Einstein's equation for energy, how much energy is locked up in a given mass, and I went into knots and so forth, self-interferences, but the energy, the universe is the physical energy is, the physical universe, physical is energy, and the energy is either energy as radiation unfettered or in mass brought together. So we have energy equals m, that's the brought together side, times this and then is modified how much energy is in there by its relationship to this speed of radiation to the second power. Speed of radiation to the second power, because we said that's the rate at which a surface wave grows. That's the second power. So then we come down to the gravitational constant, and we come back again to our friend the second power, which I spoke to you about, this exponential 2 that shows up, which has something apparently to do with surfaces. And we find here is a system growing rationally, beautiful rational number, absolutely in relation to this frequency of the second power, which characterizes both gravity, gravitation constant, and the radiation constant. It gets to be very, very intriguing. As we go on with these kind of numbers, the 12, 42, 92, I'd like you to add up those numbers, 12, 42, 92. Why am I interested in that? Because, incidentally, I'm going to stop for just a minute, double back myself just a little. I'm going to get into a little more discussion about nuclear phenomena. I have one ball is not a nucleus by itself. I'm not going to start triangulation of balls. And here's one ball, and then I'm going to have two balls tangent like that. There's no ball at the center of the group. And I have another ball, and another ball. No ball at the center of the group, is it? I'm going to have another ball. There are balls. For the first time, there's a ball at the center of the group. It's going to be red, nucleus. Now, let me have another layer. This is the center. There's no ball at the center of the layer. I would have another layer. No ball at the center of the layer. So I need to have one more layer. I don't know whether I can really work this or not, but try. And suddenly there's another ball at the center of the layer. So it went no, no, yes. No, no, yes. No, no, yes. It's not yes, no at all. It's a very interesting kind of periodicity. So it was not until we got to here's a frequency phenomena. Just pay attention to this triangle in here. And we have, while you see four balls to the edge, it's a three frequency. 1, 2, 3. 1, 2, 3. 1, 2, 3. It's a three frequency system. Three frequency then has a ball at the nucleus. Therefore, as I begin to build up the vector equilibrium, and each edge of the vector equilibrium shows four balls, it's a three frequency system, and at that level there's a new nucleus showing, but it's not a nucleus because it's just showing on the surface. There's a nucleus at the center of the thing. There's a nucleus on the surface, but it's not a nucleus till it too is equally enclosed with the original nucleus, which apparently always gets two good layers of its own. So this one's going to have, so I can get a frequency, 4 frequency, 5 frequency. After I have 5 frequency, I suddenly am really enclosed and have a new nucleus vying with the original nucleus. So we find that this nuclear idea is one that which the first nucleus shows up at the layer. First layer was this 12, 42, no nucleus. Not until we got to 92 did we have a new nucleus showing. But we said wasn't one. It too would have to have another layer on the outside of it here. Still isn't a nucleus. It's not really a nucleus till it gets then to this one, and then it suddenly is really enclosed. You see, this 92 is in the enclosure point. This number 92 becomes a very important number, and I'm going to take the 12, 42, and 92. I want to add them up. This is not including the ball at the center of the system. It's just the layers. We finally have 6, 1, 9, 10, 146. That's the number of neutrons in uranium, which is chemical element number 92. That gets me very impressive suddenly. And then they find that you add to the 146, this is 92. There is a matching, always 92ness. There's always a 2ness in the outside of the system. So there's another 92 that comes onto here. That gives you 8 uranium-238. So if you want to make it feasible, you knock out fog. Well, these numbers suddenly get to be very intriguing. There's compatibility with both, accommodating both Einstein's radiation and the Newtonian gravitation, which is what Einstein hoped very much. It's your unified field theory suddenly showing up. I want to realize I'm saying these in a really very kindergarten kind of way, but it's the truth. So you imagine how excited I became about energetic geometry, so I began to get into it a great many years ago. Because I'd like to just recite once more, as a little boy, there are things that I was always being told, never mind what you think, pay attention to the teacher. And I was trying very hard. But the teacher would say things from time to time that, that I couldn't help have some reservation about it. I never forget going to learning first fractions. And we learned all how to manipulate fractions. Everything's going great. And one day the teacher said, I'm going to show you a better way of doing it. We wondered why she didn't give us a better way the first time. She called decimals. So she had a 0.125, that's 1/8, and 0.25 is a quarter. 0.333 goes out the window and over the hill. Every once in a while things went out of the window and over the hill. Other things stayed in the room. I wonder if she really knew what she was talking about. It didn't seem to me a very good classification. So I began to really ask myself a lot of questions, and particularly when it came to geometry, because I love geometry. And she had a point put on the blackboard, said it doesn't exist. So she went. I said, I'm going to take a number of these points that don't exist, put them side by side, and that makes a line. And said, that doesn't exist. She wiped that out. Then she took a number of these lines, didn't exist, made out of points, and laid them parallel to one another and got a plane. Said, that doesn't exist. She wiped that out. Then she stacked a number of those planes made out of, that didn't exist, made out of lines that didn't exist, made out of points that didn't exist, up like this. It says it's a cube, now it says exists. So I wonder how you get existence out of non-existence to the fourth power. And so I said, if it exists, I said, how old is it? She said, don't be naughty. And then I want to know how much it weighed and what its temperature was. Because the word existence, these had something to do to me with existing. And in fact, she couldn't identify it. It was an absolute ghost cube of her imagination. Now, I then want to come back to something else I call the dilemma of mathematics and its imaginary phenomena. And we find the mathematician then talking about lines and lines that go to infinity. And from an Einsteinian viewpoint, that doesn't make much sense, because I said he's entirely operational. He's never been to infinity, so he doesn't say that. He found that all energy was in finite packages and seemed to be an aggregate of finites. And he's not talking about any kind of infinity at all. But we find the mathematician got what he called it to me. He tells me a beautiful, a straight line. I said, I'll draw it. And he takes his ruler and the board, he sticks it up. I looked at it. I said, it's really, really quite crooked. Look, see that chalk is up and down. He said, you're not in the spirit of mathematics. This is just an imaginary straight line, absolutely pure. So I said, I don't know how the word imagination comes out of experience. And the word line was invented by me for an experience I was having, either trajectory of leaving some smoke behind, or I'm leaving some chalk behind, or I've taken a chisel and taken something away. I've left a tracery of my actions. And those are always going to be very, very crooked. Anyway, the master said, I mean a line of sight. Get straight. Get yourself now a surveyor's transit. I said, all right, we'll put the surveyor's transit on the sun. I said, just kissing the horizon in the evening. And we find the sun hasn't been there for 8 minutes, so you're looking right around the curvature of the Earth. And the master said, you just apparently don't want to get in the spirit of mathematics. You never will understand it. So I finally came to a discovery which I find begins to work fairly well. I'm going to take I spoke about Boole the other night, Boole developing his Boolean algebra when you can't find a logical way, take the most absurd way. And you take the most absolute absurd you can get, and you then get something a little less absurd. You gradually get working towards something that might be reasonable by elimination of the absurdities. At any rate, I'm going to take a deliberately non-straight line. Instead of saying I have a straight line, I want to be ever sure of it. So I take a piece of rope, which is obviously curly, it's all twisted. I'm going to take and one of the definitions of straight lines is it never returns upon itself. So I'm going to take the ends of my rope and deliberately splice them together. So I have a most clearly, deliberately non-straight line, either along the local surface or the ends coming together. It is a closed circuit. And I'm going to take that piece of rope, and I find that I'm going to take any two parts of it and put them side like this and put a clamp on it. Then I'm going to massage the rope from the clamp on like this, keep massaging it very evenly. And I come to where it turns around very sharply back on itself. It's a tight little radius, and I keep it pinched for it. And I make a mark, I put a little red ribbon on that turning point. Then I go to the clamp and massage the other way, and come to where it turns around again. And we get just as close as I can in the middle of that arc and put another ribbon on. Quite clearly, I've now divided the rope into two parts that are fairly reasonably 50 each, about half of the rope. Heisenberg makes it absolutely clear we can never be exact, so that we just only struggle so far. I'm very content that I've taken unity and divided it into approximately two parts. Now I'm going to take each one of those parts between the ribbon and pair them up the same way. And I'm going to get a quarter points. I'm going to do the same way. Keep halving the distance in between points. We're not increasing and multiplying error, we're simply continually locally halvings. So that each one is a reasonably good half. So we get down to 16ths and 32nds and 64ths and so forth. All nice, clear marking distinctions so we know which point we're dealing in. Now we're going to go to the wall, and we're going to put up take some nails, and I'm going to put a nail on the wall. This is the wall we're looking at over here. I'm going to put a nail here, and I'm going to ask you to, I'm going to take the piece of rope and put the first marker on here. I'm going to ask you to really hold it nice and tightly, and I'm going to go to the quarter marker, a quarter way around the rope, and I'm going to pull it tautly from you. So it swings as a radius here, and I can put in another nail anywhere I want on that radius. So this distance between this one I know is 1/4 of my rope. Then with the same thing, you're going to come down here, another quarter point, and I can string it any way you want in here, and so I say let's put it in here. So we come should be about over here. So then I'm going to get to another quarter point. I got somebody holding and got holding here, so there's a slack piece in here, and I come down to the marker, pull it tautly, and put in another nail. So now my rope is stretched over that, and the rope is got a diamond. It's an equilateral parallelogram. You're very familiar with that, and there's nothing you've learned in geometry that as far as just playing games of lines that I will not go along with. It's fine. This equilateral parallelogram. But I have very clearly already marked on here other points. So I'm going to take the 1/8 points. And I'm going to take the rope off of here, off of this point nail here, and pull it down firmly. And so the rope is now going to come down to here. And I'm going to take it off this nail here and pull it firmly up like that. It's going to come up to here. We've got now two parallelograms. And I can eliminate this one out here. This is the same piece of rope now. It's 2 diamonds end to end. And it's very easy, absolutely all the way through. It's all equilateral parallelograms, holding absolutely true. Same length between A and B all the time here. Now, there's no trouble at all to do that again. So each time I'm going to have in here, and we eliminate this. Now we got 4 diamonds in a row. Here it goes. In no time at all, when we get to 36 and 64 and so forth, we get down where every time I do this, I halve the distance. So what we have now is this baby. And those vertexes are getting close. But it's always the same length. It's always it's deliberately non-straight line, but it's getting straighter and straighter. By the time you get to the 64th and so forth, almost no time at all, begins to look like a straight line. And it gets straighter and straighter. And I have a way of getting straighter and straighter, which the mathematician didn't have. At least I've got a progression towards straighter. He didn't really have any sort of making time to say, I got a better idea of a line of sight or something like that. He didn't have any really methodical way of getting there. But I know it's non-straight. So I'm going to be able to then get a line for the mathematician, which is, I can really prove mathematically, is probably a little finer than any straight line he's ever used. But I know it's deliberately non-straight. Now the physicist, when he wants to get the student feeling wave, we get into quantum and wave, we only want to feel wave. One of the first tricks he does is to put a nail in the wall and fasten a rope to it, and stand over here and you throw a whip into the rope, and it goes to the wall, comes right back and stops. It's a fundamental calculus of wave, comes back where it stopped. Beautiful thing. What's going on here? You then, from A, you whip here from A, it goes out here to B, and comes right back to itself. It's a wave, see it? Now when he said, I meant a line of sight, that is always wave phenomenon. This is a line of sight. Now I'm really able to give him, show him what his real line of sight really was. It is a wave. Physics had found no straight line, found only wave. Only could it. So I said, Mr. Mathematician, now I'm giving you a tool that is much more reliable for you, but just never kid yourself again, never call a great straight line. It's simply dealing in wave phenomena, and now we can go on to all the geometry you ever did. This is the first time the mathematician really began to be a little friendly with me, because he has not liked really being excluded from the experiential club of the physicists. And his salary is very much smaller than the physicist. Now, this brings me then to, I've given you some agglomeration of spheres, and there are many things I would do if I had more models around me, but I'm fairly limited in my choices, things I see, because I see one frequency and so forth, and not agglomeration. I've already done octahedrons and tetrahedron with you, and you felt those and felt those grow. And you'll find if we take tetrahedra, I do get 4 tetrahedra together but no nucleus, right? If I however then make another layer, I can have a tetrahedron where you see 3 balls on an edge with actually frequency 2, and its number of balls are 4 on the top and 6 on the bottom. There are 10 balls. 6, 10. Then if I have another layer, it gets another 10, it goes to 20. In this layer, however, the 20 layer, no, when the 20 altogether, this is the 10. There you had 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's where the nucleus begins to show up again, the 10 layer. So on this surface of the tetrahedron, on each of the four surfaces, you see a new nucleus begin to a nucleus was first, because the tetrahedron didn't have a nucleus of its own. I'll then have to put one more layer, and the next layer will have 15 in it, so it goes to 35. No, not 50, yeah. It does have 15. 1, 2, 3, 4, 5, 6, 8, 9, 10, 11, 12, 13, 14, 15. There's 15 balls in that. When you do then, for the first time, we have a nucleated tetrahedron. So there is a nucleated tetrahedron. And the same way we can get then to how to get an octahedron with a nucleus. So I find that when I'm getting into dealing in the tetrahedron, I'm dealing in a very... Suppose we took 2 off of here. No, I'm not dealing in the volumes. I'm really just dealing in the numbers of balls, so I can't talk about it. What would be dealing if I were dealing in tetrahedral volumes, the way I was doing with the... No, I'm still not doing this right. 4, 8, 18. Take off 2 here. 4, 8, 18, 33, 'So what have we got? This I would have 2 to the second power, wouldn't I? And 2 to the third power? No. This seems to be 18 times 9, doesn't it? This factors out as 9 times 2. This is 2 times 4, and this is 2 times 2. 2, 4, 9. My frequency here, let me see, in this ball, this will be better. Frequency, and where we have then as a nucleus in it, is 1, 2, 3, 4. Frequency is 4, and I had and the vector equilibrium was 10, 2 plus 2. 2 times 10 times frequency to the second power plus 2. Because this is 2 times 5. That's 2 times 5 times frequency to the second power plus 2. And we would have, if I'm right, this is 4. So frequency is 4. Second power times 2 plus 2 plus 2. I think that's just right. Second power is 4. 2 4 is 8. Sorry, I'm being very bad. I know that the numbers of the balls in this I did the other one entirely by layers, and I've been really bad because there is a nucleus now. There are 32 balls here, rather than 33, and that was getting me in some trouble. Okay, because we got 2, 4, 8. This is a 3, and this is a 4, 3, 2. 2 plus 2 times 2. Then, whereas the same formula then for the number of balls in the outer layer of the nucleated tetrahedron, in contradistinction to the vector equilibrium where it was 10 times frequency to the second power plus 2, it comes out 4 times frequency to the second power plus 2. But the 4 is, as the 10 was 2 times 5, the 4 is 2 times 2 times frequency to the second power plus 2. That's the number of balls in the outer layer when it's tetrahedral. When you do it octahedral, the number comes out 4. As we have even fine with this. And there's a multiplicative 2 here, and I take that out, so that gives me there's a prime oneness. We find tetrahedron coming out the prime number 1. The octa comes out the prime number 2, and the cube is a prime number 3, and the vector equilibrium in the icosahedron is the prime number 5. These are the first 4 prime numbers, 1, 2, 3, 4, 1, 2, 3, 5, of all numbers, and we find, as we're going to go on here, some very interesting things of the really number. It goes up only to 4. It's really like the 4 of the vertexes of the basic structural system of the universe. We get 4 positive and 4 negative. We get to the number 8. I'm going to try to show you that. I'm sorry we don't have the good pages and the models, everything all printed out, but we will come back with our video. We have all these pages in synergetics, so we'll be able to take pages from synergetics and reintroduce them into the video. May I have your chart then? May I have your chart then? Wonder if I could sit on here with that. It's a very bright light there, and everybody can see it a little better. You'll find this is the synergetics hierarchy of topological characteristics of omnitriangulated polyhedral systems. And you must remember, when you're talking about the cube, that in order to have a cube, you must put a diagonal in its face. So it has to, they always must be triangulated. These are structural systems. In other words, they're absolutely stable in doing what they're doing. And there are a great many other items on here, but this is where we begin with the vector edge tetrahedron with a volume of 1. The octahedron has a quality of always doubling on itself, which you may remember as I pump this down here. Octahedron seems to occur in double bond always. You see two octahedra congruent one with the other. The more you get familiar with synergetic geometry, you realize that this is fundamental for the octahedron, so it occurs twice. It keeps showing the number 4 where it really represents the prime number 2. This doubles itself. And we find then this is this hierarchy, and I'll go through then the vector edge tetrahedron and the vector edge octahedron, the vector cube and so forth, and vector equilibrium. We find then the vector edge icosahedron combined volumetrically with the vector edge cube, where the cube likes to be edged this way. Its number comes out, the two add together come out the number 27. And we find all the vector edge octahedron and so forth. These are all beautiful rational numbers. Now what I found that I spoke to you that Euler didn't think to do was to identify the plus 2-ness of his equation with poles. So I find that every system always has two. Every system is inherently, as he himself knew, is rotatable, and there is a neutral axis of the spin of the system. So that you have to have, now two vertexes have to have the function of being poles. So when I take the Euler formulas, which nobody had done, and automatically subtract 2, take out, let's go through some of these. The tetrahedron has 4 vertexes plus 4 faces, equals 6 edges plus the number 2. 4 plus 4 is 8, and 6 plus 2. The octahedron, we have the 6 vertexes plus 8 faces, 14, equal to 12 edges plus the number 2, 14. Or we get to the cube, and it is now triangulated, so it has 8 vertexes plus, instead of 6, they have 12 faces. That's 18, equals then it's 18 edges, the plus 2. We keep coming out all right. Now, what I did is to take all the formulas as given by Euler, and no topologist looking at this recognized some further order in it because they didn't take out the 2 vertexes for spin. But I now take out the 2 vertexes to spin. And that leaves me for the tetrahedron, 2 plus 4 equals 6. And I got 2 taken out for poles. This leaves me 4 plus, an octahedron is 4 plus 8 equals 12. The vector equal, the cube is 6 plus 12 equals 18. The vector equilibrium is 10 plus 20 equals 30. The icosahedron is 10 plus 20 equals 30. Now each one of these then is coming out in even numbers. I find then, because they're all even numbers, I can divide them all by 2, so I try that. So I get, instead of, for tetrahedron, 2 plus 4 equals 6, I get 1 plus 2 equals 3. That's a very simple kind of relationship. 1 plus 2 equals 3. Then the next was the octahedron, and that had been 4 plus 8 equals 12, so I divide that by 2, and I get 2 plus 4 equals 6. Let me write those down. The first one I got 1 plus 2 equals 3. Now I'm getting 2 plus 4 equals 6. Then I get to the cube, and I've got 6 plus 12 is equal to 18, so I said I divide those by 2, and that gives me 3 plus 6 equals 9. We said that 1 plus 2 equals 3, 2 plus 4 equals 6, and 3 plus 6 equals 9. So what's the next one? The vector equilibrium, or the icosahedron, which was 10 plus 20 equals 30. I divide that by 2, and I get 10 plus 20 equals 30, and I get 5 plus 10 equals 15. Now these are very interesting numbers because you find 1 plus 2 equals 3, you couldn't have something simpler. But the next one, 2 plus 4 equals 6, is 1 plus 2 equals 3 times 2. And the next one, 3 plus 6 equals 9, divided by 3, and it's 1 plus 2 equals 3. And the next one is 5 plus 10, divide that by 5, and you get 1 plus 2 equals 3. So we have in every case here, 1 plus 2 equals 3 times tetrahedron is by 1, octahedron is by 2, multiplied by 2, and cube by 3, and icosa or vector equilibrium by 5, those first 4 prime numbers. We have then, I found there's what I call a multiplicative 2 and an additive 2. There was an additive 2 of the poles for every system in the universe. There was also multiplicative too, because there was a concave and a convex. There's an inherent duality of this congruence of an inside system, because concave and convex are not the same. You just have to realize you have a fundamental congruence of a macrocosm and microcosm. There's negative and positive, some congruent there, but you can't separate them. But the concave radiation impinging on concave concentrates the radiation on convex, diffuses it. So, and energy-wise, you find they're absolutely not, they're just not the same, yet they're congruent, you can't separate them. So this is what I call then the duality tunus. So we find every system has a duality tunus, and it has a plus tunus of poles for axial rotation. When I take that out, then there's a constant relative abundance for every vertex, 2 faces and 3 edges. And the only difference there is a prime number, that a tetrahedron is a 1, an octahedron is a 2, a cube is a 3, and a vector equilibrium or icosahedron are a number 5. Now this gets to be very, very exciting. And I gave you frequency the other day, then I showed you a series of triangles. If the edge reads 2, then you have 4 triangles. If the edge reads 3, that edge is frequency. So I have that frequency, the second power, and remember it came out all right. It's triangulation. So as we get into any of these, we find they're all triangulated, so simply increase the frequency. So then in addition to the duality tunus of every system, a polarity tunus of every system, that's the plus tunus. The duality tunus is a multiplicative tunus. The multiplicative tunus, an additive tunus. Then there's these 4 prime numbers, and everything else is just frequency, second power, times that frequency, whatever it is. This tells you all about all the structural systems in the universe. And which is very, very exciting, because then you find, because there is a duality, you do have to have the multiplicative tunus. Therefore, you find that for every positive one vertex, you're going to have a negative one in the system, rather than opposite. So I said 1 plus 2 equals 3, but instead of that, I've got to say 2 plus 4 equals 6. That is, quite clearly, all the numbers of points in the universe will be divisible by 2. And for every point in the universe, there are always going to be 3 vectors, because there are always going to be pairs of points. Then you're going to always have 6. I've said the other day, then there's 6 basic, because there's 6 vectors always. With every event in the universe, there's 6 vectors. And those are the 6, and each one is positive, negative, so those are my 12 degrees of freedom I gave you the other day. I want to see how really beautifully these things begin to prove themselves up and down. There's a very swift simplification of great comprehensive accounting as we get into the synergetics hierarchy. Everything coming out rational and whole. And I was so really terribly impressed when I was a kid by the fact that whereas the chemistry was always associating in whole, rational, low-order numbers, associating, disassociating these beautiful whole, rational numbers. Physics was always coming out with irrational numbers. And I felt that what was the root cause was that we were really using yardsticks that were not the logical yardsticks. That we come in the attic window and we're trying to measure all the rest of the windows by the attic window or something. So it just was an unreasonable original story. So I see that man then feeling monological, thinking it's a flat earth. I can understand him making cubes, and cubes were very nice, so they seemed to fill all space. They were building blocks. Tetrahedron wouldn't all by itself, so I had to cast that out. But it was flat earth anyway, so we might as well just try out cubes, and that's the way to divide the universe. The minute you get into stratical, you're going to realize they're not going to work very nice, but you could have this triangle on the surface, and then it went to the center of the sphere. You get a beautiful tetrahedron right there all the time. Now, this chart goes on to get into really these complex forms that we're getting here. So they're all superbly accounted. You'll never get in trouble. But all of them are some combination of those first 4 prime numbers. That's all you have to have. And the minute you get a 3, you know you're dealing in cubes. That's all it is. It's always going to come out of it. Now, I would like to have a first break, if I may. It's been moving around fairly heavily. I'm going to run a few slides now that confirm some of the things I've talked about earlier, but just ask you to imagine. And the ones I'm going to use now, I'd like to have first, Bob, that the half octahedra. You see, 2 1/2 octahedra and a whole octahedron. And you remember the octahedron has a volume of 4, so each of those half octahedra has a value of 2. And each one of those, remember, nests neatly into the square faces of the vector equilibrium. May I have the next slide? Now you see a 1/2 octahedron cut into 4 1/8 octahedra on the left-hand side there. The gray ones are, each one of those are 1/8 octahedra. And they have an equilateral triangular face on the outside, but at the center they have the 90-degree angle and subtended by 245s outside. Next picture. Now you can see that 1/8 octahedron extracted from the octahedron, coming out from its center of gravity. Next picture. Now I'm going to take, there's a round tetrahedron and 4 1/8 octahedra. I wonder if that picture could be elevated. And right, addressing the 4 1/8 octahedra, the equilateral triangular faces of them, which have been their outside faces when they're in the octahedron, to the equilateral triangular faces of the 4 tetrahedrons, equilateral triangular faces. And together they make the cube. The next picture, can you see this coming together to make the cube? Next picture. Now, I'm going to cut the pictures out. Just hold on to that for a minute. You see a great circle. I'm going to remember how I like to be sure you have limit cases. You come to the end of things. I like to deal in, and there's no question about our dealing in unity. And here is a circle. And it's very interesting that a circle, you take any circle and take any 2 points on that circle, beside you bring them together. They make any 2 points, and it'll always make, if you do make the edge, it always goes congruent, no trouble at all. And then you fold it, and you got 2 half circles, all right. This is very, very simple kind of folding. I'm now going to I want to do something. I'm going to try to divide these into thirds. So can you see how I'm taking this part and make it match as two halves, all right? Then I fold back on the other side just the same way. I've now divided my circle into approximate six equal parts. Now, I'm going to do that for several more great circles. There's a half. Again, I'm going to try to make that just as even as I can between the 2 halves. This folds back out the corner. Now this way. And do that 4 times altogether, taking 4 great circles. I'm taking 4 great circles because of the interest we really have in that 4ness, and 4 great circles. Then the great circles are a plane. You want to remember what a great circle is. A great circle is a line formed on a sphere by a plane going through the center of the sphere. Now, I think I had mentioned to you before that the great circle is the shortest distance between 2 points on the sphere. Remember how I took the latitude of 80 degrees north latitude and superimposed it on the equator, crossing the equator? You remember that? And it's a shorter distance between A and B, where the little circle crossed the big circle. Much shorter distance to stay on the equator than to go off the little detour of the circle. That's a typical of the great circle to be shorter distance. So the word geodesic in mathematics, synergetics, means the most economical relationship between events. One event would be a bird flying in the sky, and the other event might be you. And I don't know why you'd want to do it, but supposing you wanted to fire a gun at the bird, which I'm sorry to say a lot of people do, if they want to hit the bird, they don't fire where the bird is, because the bird's in flight. They fire where they figure it's going to be. And you find there's, while it's not much gravity effect, there is always a gravity effect, so that the firing is pulled a little like this by towards the earth. It may be infinitesimal to your eye, nonetheless there's such a measurement, and of course you've got to go right towards the earth. So we have then the bird is in flight, and there's always some wind. There's also a little inequity to the surface of this bullet, and so one side a little more drag than the other. If you take which they often do, during World War II, the great many photographs taken at night of two airplanes in a dogfight where they were using tracer bullets, and the pictures usually taken from another plane of the two. And it doesn't make a difference whether you took it from the plane, one of the planes, or another plane. What you saw is absolute corkscrew fire. That is the shortest distance, most economical distance between these two was a geodesic line, and they're not straight. They're always curves. There would be, for instance, the Earth revolving for the sun very rapidly. We have a vine growing on the Earth, and the top of the vine growing each day, and it's very flexible, and it wants the sun. So in the morning, this little tendril coming up, and the leaf opens to the east to get the sun. And then as the day goes on, the Earth's revolving, and the Earth is revolving, but the leaf keeps penetrating towards the sun. So in the afternoon, it seems to be reaching towards the sun. And then tomorrow morning's over here again. That's why they are spiraling up this, reaching this two-way. But this leaf was always much nearer to the sun than were the roots. And if you really take a total picture of that going around the total sun, revolving all the total, it describes a line very much nearer to the sun than the rest of the Earth. So these are geodesics. They're interesting things. But so great circles are the shortest, most economical distance between points on a sphere. Therefore, great circles are called geodesics. I made 4 of these great circle, folded them up. You saw me in the thirds, and I'm going to put them together using bobby pins. I put one. They get 2 tetrahedra here. And another one. Wow. We now have our 8 tetrahedra of the vector equilibrium in pairs. I'm going to take, there's 2 of these. See, they sit like this. They tend really to come together in a sort of natural way. Put a bobby pin there. Another bobby pin here. Very neat form it gets to be. Then put 2 more of these together. Okay. take those two, let them sit on top of here. To get some more pins. Other pair. Now these are absolutely perfect because they hold great circles and nothing extra in them. And so it begins to be a little tension as you begin to pull them together. Quite a little gap there. Bring it together, and sure enough, the slack is in there because it's there. Now suddenly, I took 4 great circles, and you see 4 great circle planes all over again. Here's one, there they are. The 4 great circles have been then folded locally, so local energy holding patterns. You have a very extraordinary thing here where you can either go completely around or you can go around locally. The same amount of energy. You can remember those 6 moves that you can make, so you can be very local holding pattern to go on and on. Now there are 12 points here, and when spheres are closest packed around spheres, these little points are where they go through and touch the next sphere. So if energy were traveling through space, through atoms that were in closest packing, we find energy follows a convex surface, not the concave. Fairly easy to understand. Just take a piece of paper and just bend it. Exterior, this goes into a little more tension on the outside, doesn't it? It tries to resist you. For tension, higher tension, and the energy follows a higher tension. We have a great copper sphere, hollow sphere, maybe 20 feet diameter, Van de Graaff generator, where you simply keep loading electrical charges onto it, and they always stay on the outside and get up to a couple of million volts, and they're easily used for making artificial lighting. But people can walk around the inside, absolutely no trouble at all. They'll never be short circuit. The energy always stays on the convex side. For this reason, when you're trying to plate, silver plate and plate metals, the convex is very easy to plate. The concave is almost impossible. You have to get your anode right in, practically touching it in order to get it flowing onto there at all. So we find energy is always following that convex. So that energy going from here to there in the universe following the convex would follow the outside of a sphere till it came to a point of the next could only get to get on another sphere through a point of tangency. And it could get on such great circles as these. And so these get to be beginnings of railroad tracks. All the great circles that go through these 12 points in this sort of fundamental symmetry are going to be the way in which energy could get from here to there in the universe to closest packed vector equilibrium. We have, I've got terribly interested in this particular device and begin to pay a little more attention to it. This is interesting. These are the same 4 planes. And once you see, remember this, our friend vector equilibrium, how you can pump that around. It's an extraordinary thing here. You can flatten it down to get all the planes congruent. It opens 4 completely different ways. And if you can flatten it any one of those ways, it comes out a different looking pattern altogether. These are typical of the intertransformability starting from our wonderful vector equilibrium. And I mentioned the other day that vector equilibrium really was the limit domain of a nucleus. And everything goes on within the vector equilibrium is unique to nuclei and to atoms. What goes on outside of them when they join up with others is unique to chemical compounding. So and molecules and so forth, where things join up. Joining as outside, this is the domain of the non-joining inside. It's very fundamental. There's these basic patterns. Now, I want to talk about other great circles. And this one is very easy to make because they are all the same, and you can do your own improvising really quite easily. But I have side pictures of other great circles. But I want you to think about what they might be. As, for instance, we have the tetrahedron, and I'd like to find symmetries in it. For instance, you might say, this doesn't seem to have a pole there, but I take a mid-edge and a mid-edge, and suddenly it does have a symmetry. Tetrahedron, supposing I were to take a knife, it's made out of cheese, and I cut parallel to this plane here, but up here I could truncate this little corner, couldn't I? And leave a little triangular unit. Can you see that? I could cut off this corner. I could truncate each of the four corners and get little additional triangles on here. If I did that, having cut, you can see where I'd cut into here, you'd find you'd have a hexagon. So I'd get 4 hexagonal faces plus 4 triangular corners. You often see that figure showing up. Then, supposing I want to take a knife or a plane, this is made out of wood or cheese, and I slice parallel to this edge itself as I truncate the edge. Can you see how I might do that? My lines would look like that, parallel to the edge. So I cut the cheese off, so I've got a little flat plane on each of the 6 edges of the cube, of the tetrahedron. And so that will leave me still 4 flat faces out here, and I could then truncate these corners. Sum totally, I could get facets on here. I could get up to the four faces already there, plus 6 facets. If I truncated the edges, makes 10. I could get 4 facets at the corners, get 14. That's 14, and these always they're opposites, so they must be in pairs. So there are actually 7 axi of symmetry in the 14ness of the 4 plus 4 and plus 6, and that 14ness shows up as 7 sets of great circles, and these 7 sets of great circles have very interesting properties. We're going to look at those, and they are really all the axi of symmetry of all crystallography. There's 7 fundamental symmetries. And let's come, for instance, to the may I have the first picture now? Next picture. We're looking at the vector equilibrium again. Remember the four great circles. Now you're getting familiar with it all of a sudden. Next picture, please. And we're looking at it made in colors. Next picture. Next picture again. This is the one where I get what I call a concave and a convex one, and you're going to find those very interesting, because I said vector equilibrium was the limit case. And if I take the vector's edge of vector equilibrium, I can bend them, make them into arcs. This means all the vertexes go inwardly a little. Or if I bent the exterior edges concave, it would make the vector, because you're shortening the lines, therefore the vertexes have to come in. It's in this seemingly straight condition that takes the most room in the universe. And those concave and convex qualities you see in that picture relate then to the first, like knocking out the central ball, and it becomes the icosahedron. These are first degrees of contraction, where you have to follow hierarchy of forms that begin to generate. Next picture. This is a little difficult. See, that's a transparent 4 great circle. Next picture. What we're looking at here now, I've tried to just take 2 great circles and cross them, and they really become unstable. They just look like this. They have a common, but they're flat. And I've tried to make then the next picture, please. There we try to make the central angles of the tetrahedron, what's called 109 degrees and 28 minutes. Where that doesn't work. You'll find that the 109, 28 is what each one of these arcs are, and they don't come out in whole great circles. Next picture. Here is the octahedron. You say, well, those are 90 degrees. Now, if you try to make those supposing I try to make a bow tie the way I had here, of 90, 90, 90, 90, 90, 90. What do I get there? 4 times 90. That's all right. That's 360. But then you find you can't make it. You have to take 2 whole great circles. Next picture, please. No, you take 6 of them. Take 6 great circles folded to make the 3 great circles. I've told you before, octahedra always appear double. They always appear congruent. So to make the octahedron in great circles, folded great circles, it has to be double. Again. So there are really 6 great circles that look like 3. Next picture. There you're looking at the octahedron. Next picture. No, that's the attempted central angles of the tetrahedron. They do not work. Next picture. Now we're looking at what are called the 6 great circles. And the 6 great circles, you like to know where they come from. Let me then take the vector equilibrium itself. Let's see what it's got. It's got those 6 square faces, 8 triangular faces. It has 24 edges. It has 12 vertexes. So if you take 12 vertexes, they will then have 6 equators. They're opposite each other. The 12 vertexes are in pairs, north and south. There are 12 vertexes that are opposite each other that have 6 great circle planes. Since I revolve it, goes perpendicular. The perpendicular bisector triangle goes square, triangle, triangle, square, triangle, triangle. And that is what the axis of symmetry gives you, 6 great circles, which I've been showing you. Next picture. This is looking at the same 6 great circles. Next picture. Oh, incidentally, you get the 6 great circles, if you want to, by take a cube and put both sets of diagonals. You have the 2 tetrahedra crossing one another inside of a cube. That gives you the 6 great circles. You find that 6 great circles then has 4 times 6, 24 triangular faces. They're not equilateral, but they are isosceles, right isosceles. Next picture, please. Now we're looking at the 12 great circles. Say, where did those come from? Well, remember there are 24 edges here in the icosahedron. So if I take the mid-edges, the 24 edges, it gives me 12 axi. You see that? That'll give me then 12 axi of spin. So this is really quite a complicated one. You see it goes through the mid-edge, corner, mid-edge, mid-edge, corner, mid-edge, mid-edge, corner, mid-edge, mid. So there's a symmetry about it. It makes it really quite a complicated. Let's look behind me there, and you'll see it's quite a complicated form. Next picture. That's another of the next picture. Another of the 12 great circles. Next picture. Now, I've come back to the octahedron, to the vector equilibrium. I had here how many? There are 6 faces, square faces, aren't there? So I take opposite the mid of each square face. With 6 of them, they give me 3 axi, and this will revolve, go vertex, vertex, vertex. It has a square section in there. You see that? I can't put my fingers here, but to make it, I have to hold on to it to do it. But this is the way it revolves. This is then what they call the 3 great circles. How do we get the 4 great circles? I go to the 8, there are 8 triangular faces. So I take the 8 triangles and take their centers of gravity, and there'll be 4 axi between the 8 faces. And that's how I revolve it on those. And there you see your 4 great circles. See that great circle? Is the triangular one again? It's always, that's what gave us this beautiful form here. Those come out of the triangular faces. So the three great circles of the square faces, the four great circles of the triangular faces. There are, what other features do we have here? Then we have the 12 great circles of the mid-edges. We have 3, 4, 6. We have there were 12 of these vertexes, so 6 of these. 3, 4, 6, 12. So 3 and 4 make 7, and 6 makes 13, and 12 makes 25. There are 25 great circles on the vector equilibrium. But 3, 4, 6, and 12, there are 4 out of the 7 basic symmetries of crystallography. And you can see how really absolutely simple and fundamental. Now, I want you to watch each one of the ones I've just done with you. Go back to the 3 great circles, which are the square faces. It goes vertex, 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 vertex. There are 4 vertexes involved, right? And then let me go to the triangular faces, and I have 6 vertexes all the time. So they go through many more. The 4 great circles go through many more stations or tangents to more spheres. This is a railroad track that gets you to more stations than the 3 great circles. Then let me take the 6 great circles where we get vertex, no vertex, no vertex, vertex. You get 2 vertexes on these 6 great circles. But nonetheless, they do transfer the main grand central station of tangency to other spheres, so that the energy can travel over the convex surface of spheres, shortest distance, because all great circles are shortest distance, are going to travel. So they can travel on the 6 great circles. Then look at the 12 great circles, mid-edges, remember? Sure enough, it goes through a vertex, mid-edge, mid-edge, vertex. So it goes only through 2 again on the 12. These are really very fascinating characteristics, but this is part of the main switching of energy in the universe. And every one of the ones I've just given you, the 3, 4, 6, and 12 are all foldable out of whole great circles. You have to do your spherical trigonometry to know what the central angles are. But once you can fold this up very neatly. And you will literally take 12 great circles, fold them up, and make the 12 great circles. You come out the continuous great circles out of these bow tie forms which come together. So which tells you that every one of them has a holding action where you can go around locally or go on and travel. But the fact that some of them have 2 stations, 4 stations, 6 stations means that they're really quite a different set of options for travel on those different sets of great circles. And one has more of them than the other. The one that has 12 has only 2 stations, so that's really 24 cases there. The one that has 6 great circles, we have 2 again, so the 12 opportunities there. So the things are not coming out the same number, I want you to realize. Now the next thing we'd come to is the icosahedron. Now I have the next picture. Here is a friend icosahedron. You see some pentagons, and right away you say this is due to that 5ness, something to do with the icosahedron. So what do we have here? We have the same 12 vertexes. So it has 6 great circles. It was interesting, there was one of the 6 great circles of the 12 vertexes. But also, don't you forget, that where you got the 3 great circles was the octahedron. It took 6 of them to do it. So it really is a 6. There's a 6 appearing twice in here, in the vector equilibrium. There's also 6 on the icosahedron. Now look what it does. I spin it, and it doesn't go through any of the stations. So suddenly, there's a cutoff. Then let me say, so what other features do you have here? The other one has squares and triangles. This has only triangles. So I have 20 triangular faces. So I have 20 faces, therefore I have 10 axi a spin. This is the 10 axi of spin here. And you find that it's a very amazing thing on that icosahedron. It keeps missing the vertexes. And then I have what else have I got? I got 30 edges, which gives me 15. And this is the only one where they transfer. Because yes, yes, no, yes, yes, no, yes, yes, no, something like that other kind of pumping you ran into. The yes, yes, no shows up quite often in basic series here. And it makes it possible to do a yes, yes, no, and a yes, no, so you don't have interferences. So icosahedron has only 2 chances. So we find the icosahedron don't, they do not carry on and fill all space. Therefore, they're not what you're getting closest. Closest packing, you only get the vector equilibrium. Then it contracted in order to be the icosahedron, so it doesn't have the contacts. Again, time and again, you want to feel this really kind of neutral condition, like a neutron without the vitality, and the one that does have the nucleus, the proton. Same critter, same number system, but just a little bit contracted. And the difference of the contraction is just a difference of an electron. So we find that this thing could not have many layers. In fact, it has to act only as an electron. It really has to be a free space actor. And it does have only one way in which it can actually ever make contact with things and get something out of the system. And that was this one, of which there are 15 of those great circles. There's 30 edges. So let's look at the slides again. And every one of those are foldable out of whole great circles. That is the 6 great circles. Next picture. And 6 great circles again in transparency. I've done them in quite a different ways, different opaques. Next picture, please. And this is showing the mathematics of it. Next picture. Same thing again. Next picture. Still 6 great circles. Now we are into the 10 great circles. Next picture. The 10 great circles. That's the 10 great circles. Next picture. There's the 15 great circles. This is a very beautiful one. 15 great circles, as large as we get. And the Babylonians discovered this long ago. That I gave you remember, structural systems, where I had tetrahedron, omnitriangulated, inside and outside, it's a system. Octahedron, inside and out, icosa. But tetrahedron has 3 triangles around each corner. Octahedron 4, icosahedron 5, and you couldn't have 6 because they would add up to 360 degrees and would not come back to themselves. It could not be a system. So it was absolutely limited. There's 3 possible cases, remember that. Now, in the I lost track, jumping back and forth in my picture. Can somebody give me a help?
15 great circles?
15 great circles, right. So the most equilateral triangles, the tetrahedron has only 4, octahedron has 8, but 20 is the largest number of equilateral triangles you could possibly have in a system, quite clearly, because they add up to more than so this is the limit case. Now, each one of those equilateral triangles, quite obviously, you can divide an equilateral triangle by a perpendicular bisector. Very nice symmetry. So you have, each triangle has 3 perpendicular bisectors, which will then divide it into 6 right triangles. There'll be 3 positive and 3 negative. Yes, 6 of them. But you have 6 then times 20 faces, 120. May I have the 15 great circles back again? The Babylonians, mathematicians, discovered then these 15 great circles. I want you to realize the difference between a spherical great circle, triangle, than a chordal, because look at the right and lefts in those. If they were flat-edged, they would be hinges, but they are arc-edged, so that they will not hinge to the side. So you find that the concave and the convex cannot rotate. One cannot take the place of the other. On the flat, they can. The positive, negative, right triangles, one is red on the inside, white on the outside. You have red and white seeming to congruent this way, but in the concave convex, they can't do it. So they're 60 positive and 60 negative right spherical triangles, which you divide unity. This is a limit case of similarity, of subdivision of unity. It's a big one. So the Greeks, the Babylonians discovered that. Therefore, this is where they came to. They were trying to coordinate time and circles, the two kinds of unity. So they came to the 60 seconds, 60 minutes. This is where the 60ness comes from. This became then to them really the top necessary number. And it included the prime number 1, 2, 3, and 5. So I just want to know, the Babylonians show this figure in the old things. It's very exciting to see it. Next picture, please. This is the 15 great circles folded, and you find that they are folded because there are 15 of them, but they make a total of 120 triangles. Each one gets folded into, divide 15 into 120, what do you get? Yeah. Well, each one of these has to be in a special fold to find that they're not. These are very nice and symmetrical. Remember, each was a bow tie, just as neat as could be. This is the model, and I have used different colors. I've used yellows and blues and blacks and so forth. And the model, these are a strange kite tails where the one tetrahedron is edge to edge with the next tetrahedron. And they come together to make tetrahedron spaces outside themselves and inside themselves. So each one of them has 4, and each one of them has, I think it is 2. No, it makes up 4 on the outside, 4 inside, 4 outside of these strange things. And they do not come together in a symmetrical manner. It's absolutely impossible to make them symmetrical. The icosahedron has these very interesting, very independent properties where it seems to peel off from vector equilibriums where everything really is passing through unit, and from there on, everything goes on as some kind of an aberration of folding up or skewing or whatever it may be. Next picture, please. Look at the 15, same. Next picture, 120 triangles. Next picture, please. These are revolving the icosahedron on the 10 and the 15. I just want to, and the 6. Next picture. There is the vector. There is the icosahedron showing all of its. What does it have? It has 6, 10, and 15, which has 31 great circles. Okay? But the first ones where you use the same 12 vertexes you had in the icosahedron and in the vector equilibrium. My 12 vertexes gave me this very nice great circle where you did have 2 vertexes you went through, so it was contact. But the 6th great circle on the icosahedron does not. It's just it's absolutely pure equator. It's great equidistance from all things. It does not conduct at all. So we take there. Remember, I had 25 great circles on the vector equilibrium. There are 25 that really match them, that are torqued or twisted on the icosahedron, and then there's the 6 additional that go around that do not touch anything. So each one has 31, the other one 25, but 25 plus 6 is the 31. The extra is 6, which do not go through any of the grand central stations. Next picture, please. Now I'm going to see if we can make this bright enough for you to see it. I spoke to you a little while ago when I handled vector equilibrium. You remember pumping up and down, and the equator was rotating, but the axis was not rotating. That's the big thing, right? Now I can make this same kind of a model. I have 8 triangles. You can see those are right. Then I can have 4 axi to the 8 faces. Those would be the same as the perpendiculars to the faces of the tetrahedron. the four axi. You can find those four axi if you want. Just go to a cube, and there are 8 corners, and they're symmetrical to one another, and take the diagonal from this corner of the cube down to that one down there, and there are the 4 diagonals between the 8 corners, and they are the same lines and same central angles as the perpendiculars to these square faces here. Because I could take this vector equilibrium and put a 1/8 octahedron on here, and the whole thing, it becomes a cube. So it's just coming from this center. Now, because that's so, between vector equilibrium, there's something I call, each one of these triangle faces has a 1/8 octahedron, so if 8 of them come together, they make one octahedron. So there's what I call an exterior octahedron, and inside these when I bring vector equilibrium to vector equilibrium, the square face touches it, there's an interior octahedron here, and there's an exterior. There are 2 kinds of octahedra that keep showing up, interior and exterior to the nucleus. And they have to do with the loanings and the joinings of atoms coming together, how you can loan so many charges one to the other. And this is where it's done in here. Now, I'm going to put 4 rods coming through common center here and weld them together. The nice shiny rods which say 1/4 inch in diameter. And I'm going to take 8. Now they're welded together. I'm going to take, instead of 8 triangles, I'm going to take 8 the automobile tires. I'm going to have this rod, then the size, its diameter will be the size of the hole through. Get little toy automobile tires with a little metal wheel at the center, and it has a little hole for a journal going through, so you can slide it onto a rod. I'm going to slide the 8 toy automobile tires onto these rods. So the plane of the tire, this is the wheel, it's over like that, sliding it in like this through its hub, at the center of gravity where the triangle would be here. So each one of those wheels will be touching the other wheel at 3 points. Can you see that? One here, there's another one here. And so the automobile tires slide in on the rods until they keep meeting each other because they're converging, so they begin to push quite hard the rubber on one another. So I bring them all in an equal distance and then tight contact with each other's surface. And then I put a little journal on the outside of the rod so they can't slide outwardly. Pretty easy to bring a little metal washer and then some tape on there to hold them where they are. So they're held in friction with the other, all the automobile tires. That is the model you see up there behind my head. Don't you have it on your monitor? Maybe that's not clear. There are then these 8 wheels, and I find then they are absolutely independently journaled, free on here. Yeah, they're touching one another. So if I put this if I hold on to this as a system, because these rods are going to stick out, and I hold on to these rods kind of independently. If I rotate one of these wheels here, then this one here has to move, and they all move. And if I rotate one, all 8 rotate reciprocally very beautifully. I can try any one of them, and I find all 8 of them is absolutely beautiful to go around and around. So this motion that you saw, I want you to suddenly realize this could be the same motion as they're rotating on each other. But this top one here is staying put, and the ones around the equator are rolling along. Can you see them? This one could go like that and then keep on going. Can you really feel them going around the equator? All right. Now, for the first time, this has a limit till you come to the ends of these hinges. But this, the one model I give you now, there are no hinges, so you keep rotating one way or the other, and the whole thing is reciprocal. Then you'll find, if we're going through these 4 pictures, I have up in the top left-hand side a little white marker. And what I do now is to take a hold of one of the wheels of my fingers like this. So I immobilize that one wheel. I take a hold of the wires that are sticking out and pull the system around the one that I'm holding on to. And there's the three touching it, just roll very nicely along. They roll right around, the ball bearings. And these ones are rolling this way, and there's three are going the other way, and there's one on the top. And so I hold this one fixed, and I roll them around, so there are out of the 8 of them, 6 of them, 3 in the southern hemisphere, 3 in the northern hemisphere, are rolling beautifully. But the top one is absolutely immobile. If I hold this spring, if I immobilize the bottom one, the top one is absolutely immobilized. And that's what you can see in these pictures I go around. Next picture. You see the marker stay up there, the same position has been all. Next picture. I'm sorry, I seem to be so much in the way of this thing. Next picture. The hands had to really stay fixed. Anyway. Now what I've shown you is, I gave you then an independence of the axi, so you can fasten them onto another system, yet the rest of the system can be carrying on. So I said every system I found always has axi, it always has an isolatable axi. This is the four-dimensionality. Now, four axi of the basic symmetry here. So next thing I want to point out too is that those rubber tires, I want you to think about them as, instead of making them nice and circular, I could have made them, distorted a donut to be a little triangular. Can you see? So that it gets look like a cam. It has, here's a circle now, begin to make it go like that. So this is a little shorter radius and this is a little bigger radius than the sides. I could make each one of those a triangle. And as there were springs holding them in towards each other, as they rotated, they would go in to the position of the octahedron. When they simply get down into this closest position of the sides of the triangles versus being on the corners of the triangles. So as I rotate the system, every one of those triangles is going to be pumping like that by just their own friction, and around they go. Now the next thing about it, I'm going to say, remember I had an involuting, evoluting donut, rubber donut? So I'm going to make each one of those triangular cam rubber tires into also involuting, evoluting. So when I hold on to one triangle at the bottom here, I'm holding on to it, which makes the one up the top do something. You find this whole thing goes through, now take a hold of one edge and start to move it around, force doing that, and the whole thing pumps like this and continues involuting, evoluting. And when you see something called turbulence, that's what you're looking at. It's a very, very beautiful thing. It was being really studied when really it's called turbulence. This is the big show. I find it fascinating that we just relatively few models to begin to be able again to do this in your imagination. Fascinating pattern, because the first time the scientists ever made photograph of the atom with the field emission microscope, it came out, you could really see the whole atom and operate it, and it is a spectral equilibrium. It's that picture you see right there. I think we have that picture in a set, and we'll find it so we put it up here tomorrow. But it's really spectacularly there. The square is a little larger. There's a sort of that kind of an aberration of the distortion. You see really spot the whole 25 great circles. Next picture. And now we're looking at the icosahedron, and it's 31 great circles. And next picture, there's the icosahedron in the spherical with the Venetian line straps. Now, say there you now have seen the symmetries of actually visually the 7 great symmetries of crystallography. You're a crystallographer. You spoke about it yesterday, the normal, but this gets to be very exciting to see. I found one of the crystallographers we were not familiar with was the 12 great circles of for some reason or other of the Venetian line straps. Now, say there you now have seen the symmetries of actually visually the 7 great symmetries of crystallography. You're a crystallographer. You spoke about it yesterday, the normal, this gets to be very exciting to see. I found one of the crystal algorithms we were not familiar with was the 12 great circles of for some reason or other, of the vector equilibrium. Next picture. Now, we're looking at the both. And this is the end of these particular slides that we are going to use. There are other slides, Mehdi, that we had put aside of reconfirming some of the things we've been over today, but we might as well let that go for this minute. I'm sure you're beginning to feel with me the interrelatedness of everything. I don't think there's anything I've talked about in all these hours now. We're getting pretty close to, I think we're about at 16 hours, that everything is continually interrelatable. And think how really different that is from all the specialization and the times when I was young, when biology didn't seem to have anything really to do with chemistry, and chemistry didn't have anything to do with physics. The utter interrelatedness kind of appearing. I'm going to bring you back to C.P. Snow and his book Two Worlds, and his book about the two worlds meant the two worlds of humanities and the sciences. And he was absolutely convinced that there was a chasm building between them that would absolutely never be spanned. It was going to get worse and worse. He felt this was really a very great warning to humanity. Must appreciate it. He then, in his book, if you read it, he attributes the chasm beginnings. He goes back to about a century and a half, to the middle of the 19th century, or the first half of the 19th century. And he points out, for instance, that in America, the Emerson and Thoreau, he felt manifested antipathy to industrialization. Snow says that. Actual fact is that I think that's a very bad example, and I'll give you a good reason for it in a minute. But then he gave a number of authors in England, because he said the literary man, the humanist, just felt he didn't like the smell of the laboratory, he didn't like the feel of the factories, that labor was being cheated and so forth. It just felt wrong. I explained to C.P. Snow asked me to come to visit him just for an afternoon in his apartment in a flat in London, England, when I was there, and I went over the energetic synergetic geometry with him, and I went back to the point where I said to you, the scientists, starting with the beautiful priestly Lavoisier set of events of identifying steam and combustion, metallurgy, out of it came the steam in the ships, and the great wealth was made by the people who put steam in the ships and didn't have to wait for wind in their sails, brought about enormous patronage of the scientists and the great funds for the Royal Society, out of which came thermodynamics. And I said that to C.P. Snow, as long as there's steam, the humanists could then go to the scientists and said, I see just what's going. You can see the steam, you can see how it goes, you can turn it into pipe, you can see exactly what it does. You feel it. There's no trouble for the humanists to describe that in a book. But when you got to electromagnetics, and you couldn't see what's going on, the humanists said, you've got to tell us, Mr. Scientist, what is going on. You must give us a model so we can describe it. We always have to describe what goes on. And that is the connection between science and humanists. And the scientists said, we can't, it's something invisible, as I told you, went into that there. And they felt a little guilty about it, but they then suddenly felt great when they came to discovering in energy studies that black body radiation had a fourth power, exponential 4, rate of change. And they said quite clearly then, nature, you can't make anything but a three-dimensional model. To them, dimension was perpendicularity. And they said you can't find another perpendicular system that's in parallel when the line's already there, therefore you can't have a fourth dimension. But the scientist said nature quite clearly is using a fourth power in a relationship. Therefore, quite clearly, nature is not using models. Therefore, we are now excused and exempt from any requirement. So we justify the position we did take. We're very lucky we took the position. As a consequence, science then, in the mid-19th century, what you and I would call in flying, they started flying on instruments, and not looking out the window anymore. And they've been literally flying for a century and a half on instruments. And this is really, meantime, when I was a kid, I was being told then that there's no model and so forth, and I felt there was something probably wrong about that. Again, it's really interesting the kind of strange suspicions I had that I'm not hearing things really quite right, like the fractions and the decimals and so forth, or the geometry arguments. What seemed to be self-evident to the geometer. I felt then that they didn't. We just get more powerful microscope. And every time you get a microscope, you can see something. Because if nature then really had a threshold, she doesn't really have models, she gets where she didn't have any models. But when we got in the area of this, the people were saying there's only mathematical equation, there was still some models, but models were not easily explicable in the terms of x, y, z coordinates. So they say, the scientists used to say to me, nature just facetious, pay no attention to those pictures you can see there. That really was a very strange attitude, but it was still there quite strongly in the time of, say, World War I and for the first, between World War I and the Great Crash. Thank you. And right, it was then my feeling that the scientists were in some way making bad starts and bad assumptions when I saw that nature was continually using models, and there was something went on and very tantalizing that seemed to be more or less orderly, and so that made me persist as I have here. Anyway, with C.P. Snow, I showed him energetic synergetic geometry, and I said to Snow, I don't think it was antipathy of the writers for the smell of laboratories and factories that made them into. I think it was strictly the scientists saying to as humanists, we can't give you a model. As C.P. Snow said, I really think you're right. So then I went over energetic geometry, which he didn't know about. I said, it is my hope that we really do have conceptuality returning. And conceptuality comes because I can make the fourth dimensional model, because we're not using up all this space around an omnidirectional clock. I've got room for 20 hours, and you only had 8. So with the 20 hours, we can get in the fourth power, no trouble at all. So when we get to 2 frequency, for instance, vector equilibrium, 2 frequency, we get to where the volume is 20 times 8, 160. You find that's 2 to the 5th power times 5. You can literally make the model of it. Right. It gets to be very exciting that we can make it. Anyway, I showed him the models, and I said all the things that they made them give up the idea of models, because I said nature would not. She was using that mathematics, but you couldn't make it in a model. I said you can make it in a model. So any kid can really do nuclear physics here. That meeting of mine with C.P. Snow was about 6 years ago, and that New Year's, when scientists are often asked to make some statements, he made a statement in England that came out in the New York Times that he was convinced by an American architect that the chasm between the science and the humanities could be closed, that he would like to change his position. Now, I hope you begin to feel with me, because I feel a deep responsibility to have you feel with me that we do really have a potential coming up here, and this is a great option for humanity, and I feel very committed to being sure that young people get a good chance at it, because I'm not going to go much more in the energetic geometry today, because I would like to keep sorting my models. So the models and the pictures we have are extremely informative, and I do like giving the pictures, and I've done it several times in advance to make it in your own brain, but I think it's better this way. Incidentally, there are the 6 great circles of the icosahedron, and that there are the 12 holes in here. Those same, I found the same 12 are the closest packing spheres there. Now, I'm going to ask for a break because in the conducting what I am doing with you, doing everything spontaneously, I do not have something I really feel immediate want to get at because I don't have the tools, and I feel a little bit of impotence about it. I would like to have a break, and there's nowhere nearly time to stop, so that if you don't mind a little more break, we'll try to get a few more slides.